Hello everyone, and welcome back to our class in Artificial Intelligence and Machine Learning in Finance. And after having talked a lot about data sources, data generation, and our introduction to the realm of ML, we've now finally arrived at the applications in finance. And we'll go through all these topics by, first of all, describing and discussing the statistical methods, and then highlighting the applications in finance. And maybe a little bit surprising, we'll start with simple linear regression, multiple linear regression, because these are the building blocks for more sophisticated models in statistical learning. So we'll start our discussion now of these different AI and ML methods. It's a little bit heavy on the machine learning methods, but we'll also see some artificial intelligence methods, and we'll discuss the statistical background and then the application. Now, all of these methods are examples of statistical learning algorithms, and statistical learning refers to the set of tools used for understanding data and explaining behavior of statistical data. And broadly speaking, we can distinguish two types of models in statistical learning. The first one are supervised algorithms, and in contrast to supervised one, we also have unsupervised algorithms. What are the differences? Supervised statistical learning means that we estimate, or we predict an output based on inputs. Very simple example. You want to predict the wage of workers based on their education, their gender, and we would get what we call a regression problem. The second problem is related to this, but it's called a classification problem, because in this case, the outcome variable, the output, is a binary variable. It's a dummy variable that takes on values 1 and 0. For example, if we only want to predict ups and downs of the S&P 500, if we now use, for example, macroeconomic variables, x1, x2, etc., and we want to estimate the ups and downs, ones and zeros, we have a classification problem. Again, same here as with the credit card data. For example, we want to forecast default, no default, or default, 1 and 0. That's a classification problem. In a non-supervised statistical learning algorithm, we want to group input observations with no output variable. So the example we have here is what is a clustering problem. We have data on customers, say age, income, education, and we want to group them to see certain clusters of customers which share common properties. For example, one group are the middle-aged men, a second group are young women, a third group is maybe old persons with low income, and we get different clusters. And this is an unsupervised statistical learning problem, because as you can see, we have no output, we have no outcome variable y we want to predict, and in this case, we have no way to see how these different clusters are different when it comes to an output variable. They only differ based on their inputs. Okay, so this is a very short introduction. Let's now turn to simple linear regression, which you probably know from your introduction to statistics. Now, linear regression is the foundation for many modern supervised statistical learning approaches. So we are now looking at supervised algorithms, meaning that we have an outcome. And in the setting of simple linear regression, we want to predict a quantitative response or a metric response y on the basis of a single predictor variable x, which means that we have a regression function y, and y is approximated by two parameters, beta 0 and beta 1, and we assume a linear relation between x and y, meaning that y is almost equal to beta 1 plus beta 0 plus beta 1 times x. We say that y is regressed on x. This is a little bit different in German. In German, actually, we switch y and x, and we say that x is regressed on y, but it's y that is regressed on x. We have two unknown parameters, or coefficients, beta 0, which is called the intercept, and beta 1, which is called the slope. Those are obviously the intercept and slope of the linear regression function. It's a line. And they are estimated by minimizing the residual sum of squares, or RSS. And what we get as a result is we have an estimate for beta 0, beta 0 hat, and an estimate for beta 1, beta 1 hat. And if we now have input data x, we can use those estimated parameters, enter x, and we get an estimate for y hat. Now, how should we estimate this regression function, this linear line? Very simply, by minimizing the residual sum of squares. So we'll start with the prediction yi hat. We have a certain number of observations with xi, and we look at this regression function, and we have those estimates y, or those predictions yi hat. We also have those observations yi, and by comparing yi and yi hat, we get what we call the ith residual. That's the error. That's also why it's called E. It's the error between our prediction yi hat and the actual observation yi. And these are the different residuals from our estimated linear regression function. If we now square those errors to make sure that a negative and a positive error don't cancel each other out, if we square those errors and we sum them up, we get RSS in equation 4, which is the residual sum of squares. It's the sum of the squared errors. Now, here you can see one very simple example based on the advertising data sample from the James Witten-Hasty and Tibshirani textbook on statistical learning. Now, you see the blue line is the regression line. We have TV and sales, TV being the predictor and sales being our outcome variable. And you see all those different red dots, those are the estimates. And actually the actual observations, and the blue line is our estimated regression line. And those small gray lines, they highlight the errors. And we now want to choose the blue line in such a way that the sum of the squared gray lines becomes minimal. This is the RSS. So how should we estimate this? Well, if you remember your statistics classes, minimization of the RSS in this case of simple linear regression leads to the well-known OLS estimator, the ordinary least squares estimator for beta 1 and beta 0. X dash and y dash are the sample means of x and y. So you take your observations xi, yi, you take the sample means, enter them into these two equations 5 and 6, and you get the OLS estimates for beta 0 and beta 1. Actually, this is done on most modern calculators. They usually have functions for simple linear regression. Okay. Now here, in this case, again, the response variable is sales. The predictor is TV advertising budget. And as you can see here, we have beta 0 and beta 1 on the x and y axis. And the red dot here is this is a contour plot of the RSS, and as you can see here, this is actually the minimum, so it's very simple to find the minimal value of the RSS for beta 0 and beta 1. Okay, and this is the three-dimensional plot of the RSS. You can see here it's a very smooth function with beta 1 and beta 0 on the x and y axis, and on the z axis in the three-dimensional case. Here we have the minimum. Okay. We get resulting OLS regressions, and we can do this in this case if we have three predictors. We can use three estimations and look at TV advertising budget, radio advertising budget, and newspaper advertising budget, and we can already see there seems to be a strong linear relation between TV advertising and sales. It looks a little less linear for radios advertising and sales, and there's probably not a linear relation here with the newspaper advertising and sales, but these are three distinct regression analyses. Again, we are in the case of a simple linear regression, so meaning that we are looking at x actually y, the outcome variable y being estimated and regressed on x1 in the first plot, and y being regressed on x2 in the second plot and on x3 in the third plot. So it's not a multivariate linear regression. It's still simple linear regression. As you remember the statistics classes, you probably know that we need to look for measures of the accuracy of the coefficient estimates. We need to assess the goodness of fit of our model. And if we assume that we have a regression function y being equal to beta 0 plus beta 1 times x plus an error, how should we assess the accuracy of those coefficient estimates beta 0 hat and beta 1 hat? Well, we have to look at the standard errors of the OLS coefficients, of the estimated parameters, because they are estimated from a sample. We do have standard errors, and these standard errors are given by equations 7 and 8. As you can see, what we need is the sample mean of x, and we also need the variance of epsilon, which is the variance of the residual terms, the error term. Okay. Now, how to estimate sigma squared, because this is the only thing we do not know from our sample. We know x bar, and we know n, the number of observations. The only thing that is left unknown is sigma squared, the variance of the residual terms, and we estimate sigma via the residual standard error. We do not know how sigma looks in the population, but we can estimate sigma based on our sample and on the sample errors. So we take the residual standard error, RSE, and we take the residual sum of squares divided by n minus 2, take the square root, and we get an estimate for the residual standard error. So that's our estimate. And what we do next, we put it into the equation for the standard equation, a standard error of the coefficient estimates. And then we get the standard error of our two coefficients. But what should we do with this? Well, if we have the standard error of beta 0 hat and beta 1 hat, we can actually construct confidence intervals for beta 0 and beta 1. So the 95% confidence intervals for those two parameter estimates are given by more or less beta 0 plus and minus 2 times the standard error of those coefficients, and we get confidence intervals. And how does this help us? Well, actually, later on we will look at significance tests, and significance tests usually work like this. You have a hypothesized parameter value. Let's say we want to test the hypothesis that beta 1 is 0. There's no relation between x and y, meaning that the coefficient is 0. So we take 0 plus minus 2 times the standard error, and we get a confidence interval. If now our parameter estimate is in this confidence interval, with a 95% probability, the parameter is not significantly different from zeros, meaning that we have to reject the we cannot reject the hypothesis that beta 1 is 0. And there's no linear relation. So we can use confidence interval for significance testing. This is shown here. For example, the hypothesis is beta 1 is 0 versus H1. Beta 1 is not equal to 0. And now we take the standard error of beta 1 hat, and we use this t statistic, beta 1 hat minus 0, divided by the standard equation. So the t statistic measures the number of standard deviations that our parameter estimate is far away from 0. If it's far away from 0, there's a likelihood that actually the parameter is not equal to 0. If it's close to 0, then actually we have to reject H1. Okay. Now, this is what we do for the parameter estimates, but how should we assess the accuracy of the model itself, assuming that we rejected the hypothesis beta 1 is equal to 0? So we cannot reject a linear relation between x and y, but how can we assess the accuracy of the model itself? We can take the residual standard error and recall that associated with each individual observation is an error term EI, or epsilon, in the population. And even if the coefficients were known, these error terms still exist, and this is why it's not a perfect linear line. If it were a perfect linear line, there would be no stochastic behavior in the data, and we wouldn't need a regression analysis in the first place. But assume that we have a linear relation between x and y, and the residual term exists, and it's noise simply added to our linear regression. Even then, we do have these error terms EI, and these error terms prevent us from perfectly predicting y from x. And thus, we estimate the standard error of epsilon via the residual standard error, which is given by taking the residual sum of squares divided by n minus 2, take the square root. And then, how should we assess this? Well, the RSE provides an absolute measure of lack of fit of the model, and it is given in terms of units of y. Problem is, the RSE depends on the scale of y. So the solution in this case is we scale it. We take r squared, which you probably know from your statistics introduction, and r squared is the proportion of variance explained by the model. So r squared is equal to 1 minus the RSS divided by TSS, which is the total sum of squares, simply yi minus y bar squared, and then sum it all up for all observations. And this gives us the total sum of squares, the total variance, and 1 minus the residual sum of squares divided by the total sum of squares gives you the proportion of variance explained by our simple linear regression model. Also note that r squared is equal in this case to the squared correlation between x and y. So actually, this is why it's already called r squared. It's the squared correlation between x and y. Okay, so this is a very short introduction to simple linear regression. We'll come back to this in some instances, but obviously we want to step our game up to multiple linear regression, and we'll look at this in the next video.